Hello everyone and welcome back to my channel Gyan Sampada. In our previous class, we studied about current voltage relation and also the equation corresponding to saturation current. And today we are going to start our discussion on semiconductor devices, and first one we are going to discuss is about the tunnel diode. As such, we know that diode is a device or electronic component which allows current to flow in only one direction. So it is nothing but unidirectional flow of current. And if we look at the tunnel diode word, we can understand that in this diode we are going to observe a quantum mechanical phenomena, that is tunneling. So based on tunneling effect, this diode is named as tunnel diode. So in our today's class, we are going to discuss about the details of tunnel diode, starting from its invention, principle, the speciality, as well as the IV characteristics, and finally leading to the application and also the pros and cons of tunnel diode. So first, about the invention. Tunnel diode was invented by Isaki in the year 1958. Here you can observe a photograph of Leo Isaki, a Japanese physicist who has invented tunnel diode. And tunnel diode is a device that can function efficiently either as amplifier or as an oscillator. And tunnel diode looks somewhat like this, where you will have an anode and a cathode terminal. The symbol for tunnel diode is somewhat like this. So it is similar to the normal diode symbol, but only difference is these two lines. Why those are there, we will study today. That is because of the special feature of tunnel diode. So as per the working range, tunnel diode operates well in microwave range also. And based on its construction, we can say that a tunnel diode is a type of semiconductor diode which is heavily doped, about 1000 times greater than that of a normal diode. The main principle behind the working of tunnel diode is quantum tunneling effect. So if we want to elaborate, we can say first, a PN junction is formed where both N and P regions are heavily doped. Under such heavy doping conditions, the contact potential is going to be very large, due to which the depletion region is very narrow and the field in this region is extremely high, and this field is responsible for the tunneling effect what we can observe. Already we have discussed in detail about tunneling under quantum mechanics section. So if you want, in the playlist you can check it out. So in this only we can understand about the construction of tunnel diode, that is, it is highly doped semiconductor material and the materials typically constitute of N-type semiconductor and a P-type semiconductor. And the main point is the doping levels are maintained at an exceptionally high degree to establish a narrow depletion region, and this is going to contribute for the tunneling. So depending on this basic information, let us understand in detail about its working, how tunneling is going to take place. And under this we will also understand about the condition where biasing is done and when biasing is not there. So unbiased case, forward bias and reverse bias condition. So as such, the impurity levels broaden into impurity bands which are going to overlap, which means there is overlapping of conduction band as well as valence band. And here the carrier concentration is very large, so that the electrons and holes are going to obey degenerate Fermi-Dirac statistics. And the Fermi level, which we write it as EF, lies in the bands themselves. So if we observe according to the energy band diagram, when the biasing is not there, tunnel diode is again a PN junction, one side it is P region, one side is N region. Because of heavy doping, the carrier concentrations are very large and Fermi level lies in their corresponding bands itself. So here we can observe the Fermi level is in valence band in p region, whereas in n region Fermi level is in conduction band. So this is how the energy band look when the condition is unbiased, that is no external voltage is applied. And if biasing is done, that is what happens in forward bias and reverse bias, we will discuss in detail in the coming slides. So let us move to the next, where we are going to discuss about the reverse bias condition. When a PN junction which is heavily doped, which means a tunnel diode, in reverse bias case, since the conduction band in the N region has been lowered by a value of E into Vb, where Vb is the barrier potential, we say that electrons in the valence band of P region can tunnel through the potential barrier and finally end up in the conduction band of N region. So as there is a movement of charges or flow of charges, we can say that current will be observed. So an electrical current flows because of tunneling. So as such, what actually is a tunneling process? Tunneling process is again entirely a quantum mechanical process, and the wave function does penetrate a potential barrier. So here, according to the classical mechanics, if the potential of the particle is less than that of the barrier, it cannot overcome the barrier. But according to tunneling effect, even if the particle potential is less than the potential barrier, there is finite probability of finding the particle in the other section overcoming the barrier. So finally, the effect of reverse bias is to introduce empty states in the N region at the energy levels parallel to those of electrons in P region. And because of heavy doping, the concentration of electrons in valence band is large and field in the space region is also large. Therefore, we can observe that very large tunneling current is going to flow. And whenever we observe very large amount of tunneling current, we say that the device cannot support reverse bias. So the conclusion is, tunneling is observed in reverse bias condition, but for its working it has to be in forward bias, not in case of reverse bias condition. This effect is not favorable. So in reverse bias, tunneling is there. Tunneling is responsible for large tunneling current. If tunneling current is large in case of reverse bias, we observe the breakdown. So if it is going to break down, then the device is not useful for application. So based on this energy level diagram, we can say we need another condition of biasing, that is forward biasing. And the most interesting feature of tunnel diode appear only in the forward bias condition, because in reverse bias condition device is not going to work because of high tunneling current. Here the current is going to flow because the electrons on the N side are able to tunnel into the empty states on top of the valence band on P side, and that can be observed in this diagram. Here also tunneling is going to take place, and let us see what is the difference. So when tunneling is taking place, it is nothing but movement of charges, means current is going to flow. But the only difference is, in forward bias condition we generally require a small amount of voltage and it is going to give a small tunneling current. And as V0 is going to increase, initially the current increases as more electrons are able to tunnel. And beyond a certain bias, we can observe that the number of available empty states begin to decrease, reaching 0. and let us say again V0 is going to increase, then the current begins to increase as the minority charge carriers begin to diffuse across the junction. So as barrier decreases in height, some electrons and holes flow over it, and this can be observed in this diagram. So V0 is the potential which is given. V0 is corresponding to the peak value, that is the maximum. So if small amount of forward biasing is done, small amount of voltage is given, we observe that small tunneling current is there. But as the voltage is going on increasing, the bands are going to rise up. So as the bands are going to rise up, the number of empty states for tunneling is going on decreasing, because if you observe, if tunneling takes place here, then this is the energy gap and the charges cannot reside in the energy gap. It is the forbidden region. That's why the available empty states are going to reduce. And again, if the voltage given in this forward bias condition is increasing, in that case the minority charge carriers are going to diffuse across the barrier or across the junction, due to which again current is going to flow. But one thing to remember is, it is not the tunneling current when large forward biasing is there. Because when forward biasing is large, we can observe that depletion region is going to reduce, which means barrier height is going to reduce and normal diffusion is going to take place. Their tunneling is not observed. And this is the main feature or details about forward biasing. What happens when the potential is going on changing. And now let us plot the IV characteristic graph which explains about NDC. NDC means negative differential conductivity, and this is the main feature of tunnel diode. Negative differential conductivity, it just means that as there is increase in voltage, the current is going to decrease. So if you observe the graph, the nature looks somewhat like this. Current is along y-axis, voltage is along x-axis, and the interesting feature of the curve is the presence of NDC, that is negative differential conductivity. And here we can observe, even if the voltage is going to increase, there is decrease in current. Why that happens is illustrated in this diagram. Let us say voltage is less than 0. In that case, we observe that tunneling is going to take place and we can say large tunneling current is observed. So this is what is with respect to the reverse bias condition. So it is a plot corresponding to 1, whereas if you move to the next, voltage is 0 means unbiased condition. We observe that Fermi level lies within the bands. So it is corresponding to the origin as the PN junction is formed, that condition. Then next, if voltage is going to increase. If voltage increases, that is in forward bias condition, we observe small tunneling is going to take place, due to which small tunneling current is observed. So as V increases, I is also going to increase. That is up till 3. Again next, if voltage goes on increasing, in that case tunneling is not possible because empty states are going on reducing, due to which we can observe reduction in the amount of current, whereas even if the voltage is going on increasing, in that case the normal diffusion is going to take place because the potential barrier is very less. The height of barrier has decreased, due to which we can observe the movement of charge carriers. So again we say that voltage is going to increase, then current is also increasing. So this is how the tunnel diode is going to work based on the type of voltage given. And the main feature of tunnel diode is this NDC region only, where we observe decrease in current even when voltage is leading. So if we elaborate this, we can observe that this is reverse bias condition and this is forward bias voltage. In reverse bias, we don't have any interest because very high current is going to flow, due to which breakdown takes place. It is not getting support. And in forward biasing condition, we have the first quadrant where initially there is a tunneling current, then empty states are becoming less, due to which after reaching the peak value, peak of current corresponding to certain voltage, we observe decrease in current because decrease in tunneling effect. And finally, after the valley point, we can observe that it is going to act like a conventional diode. Main feature is this negative differential conductivity or negative resistance region, that is NDC region, and this is the IV characteristics for a tunnel diode. And a tunnel diode in NDC region can be used either as an amplifier or as an oscillator in an electrical circuit. And moving to its efficiency, the efficiency of tunnel diode depends on the ratio of peak to the valley currents. Peak current is this IP, valley current is corresponding to this change. So it is nothing but the starting and ending values of current. And this ratio can be made as large as 15 by heavy doping, and this may lead to a large peak current. Whenever heavy doping is done, this NDC region is going to enlarge. So if it is enlarging means the peak value of current and the valley current is going to increase the range, due to which the operating range is going to increase, which means efficiency is going to increase. And tunnel diodes have been made of silicon and gallium arsenide, and as the tunneling process occurs instantaneously, the tunnel diode can operate even at fairly high frequencies, even at we can say 10 gigahertz of frequency. And if we want to compare this tunnel diode with respect to the normal conventional diode, the nature of IV characteristics is like this. Here we can observe that for conventional diode, there is forward current after the knee voltage. Then in reverse bias condition, very low amount of current is going to flow even for high values of voltage, and finally we can observe there is a breakdown. And in case of tunnel diode, initially at lower reverse voltages only we can observe high value of current, and in forward bias condition we have the NDC region, and the graph from 3 to 4 it is almost similar to the conventional current. Main region is this 2 to 3, that is the speciality of tunnel diode. And after this, let us glance once with respect to all the biasing condition. If it is unbiased condition, we can observe no empty states are possible, due to which no tunneling takes place. Next, let us say a small amount of forward biasing is done, due to which small tunneling current is observed, and even if it is increased further, then the bands are going to shift, due to which tunneling is going to become maximum, reach its peak value. Then on further increase of voltage, we can observe that all the states are going to be filled, and finally the empty states are going to reduce because of the shifting of the band, which means the barrier height is going to reduce because of the forward biasing voltage, and that is observed as the NDC region. So tunnel current starts decreasing, and finally on further increase in forward voltage, we observe it is going to act like an ordinary PN junction diode. So to glance over it, if it is a normal PN junction diode, we can say the charge carriers which are having the potential greater than the potential barrier can easily pass, whereas which are having lesser potential than the barrier, they are not going to overcome the barrier. But in case of tunnel diode, we observe in the similar condition even if the charge carriers are having lesser potential when compared to the barrier height or barrier potential, there is a finite probability of flow of charge carriers across the barrier. And this itself is the reason for naming this diode as tunnel diode. So how, based on different types of biasing condition, we get the IV characteristic of the tunnel diode is clear. And now let us move on to the applications of this semiconductor device. As such, the tunnel diodes are extensively used in various areas because they have a high speed operation and also they have the ability to function at microwave frequencies. So some of the important applications we are going to list today. First one is as an oscillator. As it is having negative resistance region, tunnel diodes can generate oscillations. So already we observed the IV characteristics. That's why frequently used in local oscillators for FM radios, preamplifiers as well as very fast switching circuits. So you can observe a tunnel diode oscillator here in the image. Moving to the next application is the high speed switching and clamping. Tunnel diodes have the capability to switch in less than a nanosecond, which makes them ideal for high speed computing systems. And also they are used in logic memory storage. So tunnel diodes can also be used in such circuits because they have their high speed and fast response time. I told it is going to be working well in microwave region. So it is used as microwave amplifier also. That is, these diodes are found in various microwave amplification application. The high frequency capabilities are going to make them suitable for such type of circuits. And then is the frequency multiplier. That is, these are used in frequency multiplier circuits where the operation is in negative resistance region of the diode. So this provides the output frequency that is going to be multiple of the input frequency. So this is the image of a pulsar, that is tunnel diode pulsar, and such a number of applications are there even in the satellite communication. Main thing is the negative differential conductivity or negative resistance region only, which is the speciality of this tunnel diode. And finally, moving to the advantages and disadvantages of tunnel diode. Firstly, it can operate at extremely high frequencies reaching into the microwave region. So this acts as an advantage. Also, we have seen already that it is going to have a high speed operation with switching time less than a nanosecond. Further, it requires low power for its operation due to their low voltage requirements. So low voltage is required, due to which it operates at lower power. Also, it has a low noise and it is suitably or relatively resistant to nuclear radiations. So these are some of the important advantages of tunnel diode. Moving next to the disadvantages. Firstly, we know that the operating in negative resistance is the main feature, and if it has to operate in that region, it requires precise control over the voltage, which can be challenging. So main point is this one only. And then comes the fabrication. Fabrication of tunnel diode is complex because of its high doping requirements. And also due to their low voltage output, they are not suitable for high voltage applications. So these are the three important limitations or disadvantages, whereas the fourth one is we have seen that tunnel diode is a two-terminal device, and due to this there is no isolation between the input and output circuits. So these are the four important disadvantages of tunnel diode, and in our today's class we have dealt with as much as possible the details about tunnel diode, what actually it is, construction of it, principle of working IV characteristics, applications, as well as advantages and disadvantages of it. So clearly, even if it is having lots of advantages, there are a few disadvantages which are to be controlled in order to make use of its negative resistance. So this is it for today's class. In our next class, we are going to deal with another type of semiconductor device, that is the gun diode. See you in our next class. Till then, stay tuned and thank you.